Well, I want to talk about Doppler radar. You always hear about Doppler radar, right? But what is it and what's the future of weather radar? Well, to start out, we have to talk about what we currently have, and this is known as the NEXRAD Doppler radar, which was actually commissioned back in 1988. Now, there was another one back in the 70s, but in 1988, the radars were refreshed, and there's one of them located in Sullivan in Jefferson County, and they're all across at National Weather Service sites all across the country. So here's how the current weather radar works. You have a radar dish inside of what's called a radome that kind of looks like a golf ball. Well, this dish is spinning and it has an antenna on it. And that antenna sends a radar beam out. So the radar beam goes out and then it starts to listen. So it has the beam that goes out, then it goes into listening mode to see if any of that beam comes back, which would mean that the radar beam would have hit something like a raindrop. So that's what we show on the news when you see the green, for example, on the radar. Well, we know it's rain, but then if it turns to red, well, that means that radar beam has hit something harder, maybe like ice, and that is hail, right? And so it comes back, more of that beam comes back because more of that beam is reflected back to the radar because of the ice. And so that's why it's a different color on our radar. So what happens here is that radar beam goes out and the dish is spinning. So what it does is it scans various altitudes. So it will start at its lowest level and it will scan around and then it tilts up another half degree, spins around, and it keeps going until it reaches the highest elevation. Then it sends all of that data back and then we're able to show it to you on the news. Well, that was great technology back in 1988 and in the 1990s, but nowadays, well, we're changing to this. Check this out. This is called the phased array radar, and they've been testing this out and using this to many degrees in the research community for years and years. The National Severe Storms Laboratory out of Oklahoma has called this the paradigm shift solution for the future. And I love this quote because if you've noticed here, a couple of things. Number one, there's no dish. Number two, well, with this, there's no moving parts. It's all electronic. Again, this is called the phased array radar. So let's talk about this. The current radar scan, I mentioned that it scans one level, right? Then it goes up and scans another level. Well, that all takes time, right? 4 to 6 minutes per radar scan. This is why during tornado warnings, we often say, look, be really careful because we may say the rotation is here. Well, that could have been 5 or 6 minutes ago, right? Very delayed, not to mention the fact that with streaming services now, you may be even more delayed because there is a delay sometimes in watching us on streaming services. Phased array radar, totally different. 1 to 2 minutes, depending again on the setup of a phased array radar. Now, we don't have those operationally yet, but that's a goal here at some point. Now, the phased array radar can scan a large area much faster than the slice-by-slice model that the current radar has. Much faster, again, as you can see here. Now, the hope is to replace the aging Doppler radars with these PAR or phased array radars in the future, hopefully the near future, but there's a lot to be decided here. What's interesting is it's both dual polarization and phased array. Okay, what do I mean by dual polarization? Well, let's dive into this here for a minute. This is what we call correlation coefficient. Now, this is just showing some snow in southwestern Wisconsin, and this is back to our classic radar. We can do this now with our classic radar. What does dual polarization mean? It means that the radar beam is not only scanning vertically, but it's also scanning horizontally. So both of those scans, so this is an upgrade from back in the 80s and 90s. This is a much more recent upgrade, the dual pole upgrade, that we will often show this during tornadoes. because this can determine precipitation versus non-precipitation targets. In other words, debris balls. So if a tornado is hitting and lofting debris into the air, we can see that on our current radars. So not to say our current radars aren't powerful. They are very much powerful. They're just not speedy and overly efficient. So let's go back to this goal here of replacing the aging radars with the phased array. So this radar, again, it's all electronic. It's one big face here. So it can essentially electronically create a custom radar beam and then be able to scan it very, very quickly. Problem is, this works great in research settings. Let me explain. I was able to see this. This is so cool. This is a phased array radar on a flatbed truck. And they take these out to scan tornadoes. Really wild technology here. But think about this for a minute. If we're going to use this operationally, and I mean, are you going to put one of these at the National Weather Service site, like where we currently have the radars? Well, you can't just have one direction, right? So you either need 4 of these, right? So because you've got to be able to scan all the way around. Well, you can imagine that's cost prohibitive, that's expensive. Or you've got to have this spinning, which means that you're going to have a pedestal on it. So there are a lot of different things that have to be worked out in order for this to become operational. Hopefully, once all of that gets decided and all of that gets figured out, and then you've got to obviously install them and so on, we would have radar that is so much faster, so much more powerful. But going back to the dual polarization that I explained a minute ago, that was a big challenge that researchers had to overcome in developing this, that it wasn't just the phased array portion, which is incredible in and of itself, right? That you literally have no moving parts and just how fast and powerful these radars are in its attempt to scan storms and do so powerfully and so accurately. But it's also, how do you get the dual polarization end of it to get working as well? And the scientists and engineers that worked on this are absolutely brilliant. So that was the other issue with this as well. And that's why I bring up the dual polarization portion, because that also had to get figured out. That has been figured out. So now the question is, how can you get this into a form that can then be deployed across the country to be able to start scanning in real time? And the sizes can vary. I mean, this is a pretty big one. You can, I'm sure, make it bigger. You could make it smaller. The bigger it is, the more expensive it is. The smaller it is, obviously, it's going to be a bit cheaper. But then you've got the pedestals. You've got to consider all those sorts of things, right, of how you're actually going to do it. So here's the bottom line. The bottom line is this. The technology is here. The technology is now. In fact, the technology has been here for a while. Most recently, the dual polarization end of this was developed. So it's being used right now in research settings. So now the question is, at some point, when can we start using it on television to better predict and scan our atmosphere? So as we always like to say, stay tuned.